Good morning, good afternoon, and good evening, everyone. Thank you for joining today's webinar on lightning strikes, techniques and requirements for well-grounded tower installations. I'd like to introduce today's presenter, Tim Wild, who is Cambium Network's Director of Engineering for Hardware Development. Tim, when you're ready, you can take things from here.
Thank you, Olivia. Good afternoon, good evening. My name is, as said, Tim Wild. I've been Director of Engineering at Cambium for a couple of years. I have a presentation on which summarizes our experience in developing systems for point-to-point, point-to-multipoint tower installations to ensure that we have a reliable and robust installation. So I have a presentation. I'll just quickly run through the topics. So we're going to talk about tower grounding, surge protection. Why do we need these things on towers? A brief look at the way that surges are created, and then why it is that the equipment is susceptible to them and we see equipment damage. There are standards that have been developed by the industry to allow us to design to these standards and to test to these standards. Then we can talk about how surge protection mechanisms work, and we look at cable shielding and then best installation practices. And then we can open the floor to any questions. So a brief bit about me. As I said, Director of Engineering at Cambium Networks. I have worked previously on aircraft electronics, aircraft accident investigation, and I guess I moved into telecoms, wireless about 25 years ago. Within Orthogon, Motorola, and eventually Cambium, I've worked on a range of products from the early days in Orthogon with Germany and Spectra through to the latest products within Cambium, Medusa, 5 gigs, 3 gigs, and also part of that journey has been making sure that we have robust protection solutions for our products, and so developing lightning protection units and so on. So why do we need surge protection? Here's a board which obviously has suffered some damage. There's a lot of damage has occurred, smoke damage, and then we can see that within the metal case of the RJ45 there, that the energy has been sufficient to actually burn holes in it. So there is a lot of energy that has to be absorbed, that has to go somewhere during a surge event. So these are high currents, high voltages that end up in the cabling, which normally connect our radios. And normally our radios are dealing with signals which are in the a volt to 50 volts for power supply, the volt or so of Ethernet signal. So once we start to induce hundreds of volts and thousands of volts onto these cables, then we're way outside the range of the normal protection that would be built into electronic devices. So again, another board where we can see a lesser extent, but we have here a board which suffered a surge, and there are numerous parts, are all labeled there, and they are on the interface between what we consider to be the the outside of the board, that part of the board that connects with the Ethernet cable, the drop cable, and the inside of the board, that part of the board which is where most of the electronics lives, and that part which is grounded usually to the case of the radio. So just a short session on, well, where do these surges come from? So we have surges being generated in the atmosphere due to lightning discharges. So we're familiar with the concept of a transformer. As shown here, we have a pulse on the left-hand side across the winding, and that then induces a voltage. And if there is a resistance across the winding, it induces a current to flow in the secondary winding on the right-hand side. The transformer is designed to do this, and so the two halves of the transformer are well coupled together. But there is just the same coupling method, albeit not as strong, between a surge occurring somewhere in the atmosphere due to lightning, and the coupling through then to our tower, our equipment that is mounted on the tower. In this case, we've got a radio on the tower, we've got a cable down to the hut at the bottom, and so there's coupling from the surge wherever it occurs, the lightning, to that drop cable. So in our lightning surge, we would have thousands of amps flowing, and that current then, just a small amount of it is induced into the drop cable. So those lightning discharges could come from a strike to ground some distance away, kilometers away from the installation. They could come from a strike to the tower, the obvious one, where the tower itself gets hit. And they could come from cloud to cloud discharge. There's no cloud to ground discharge necessarily. It's just between clouds, sheet lightning, as we sometimes call it. All of those can induce a voltage, a current into our cabling. So there's our transformer. The coupling is nowhere near as good as it is on the transformer, but there is coupling nonetheless. And when you have thousands of amps flowing somewhere, then you only need a small amount of it to be coupled. So then we have the question, well, why is the equipment susceptible? We have our radio mounted on a tower. What is it about those surges and how they occur that causes the damage within the radio? So typically we'll have tested our radios in the lab using surge generators. There are conformance tests, which I'll come to later, which do this formally, but we would do informal testing prior to bringing a product to the market. And typically we would use a 2 kV surge, 2 kilovolts, applied to the drop cable with the radio itself held at ground potential. So what we know then is that, having tested that and having made sure that the isolation barrier between the primary and the secondary of the Ethernet hasn't been breached, we know that our radio is capable of withstanding 2 kilovolts, and that in a lot of cases may well be sufficient in less exposed situations. If we have a surge which exceeds 2 kilovolts, then we have a problem. because the transformer itself will break down, and then we have an uncontrolled current entering the rest of the radio, and that's when our damage occurs. And this is a problem not just at the top of the mast. We have exactly the same issue at the bottom of the mast at the equipment hut, or if we're looking at a residential situation, inside the customer's house. So the standards that apply, if we're looking at how we set up how we do our testing, 61000-4-5 level 4, trips off the tongue. This is applicable to tower mount equipment. So what does that standard say? It says that you take your equipment under test, you use a surge generator then to directly couple the surge into the cabling into that radio. So in the diagram here we have a capacitor which is charged to 4 kilovolts, a switch that we close, and then the voltage 4 kilovolts is applied via a 15 ohm resistor and then 8 25 ohm resistors directly onto the Ethernet pairs in the Ethernet drop cable. So that causes a current of around 200 amps to flow. So in the example that we have here, we have a protection unit sitting ahead of the radio, and the surge generator, then the current from the surge generator will go into the drop cable and will be intercepted by the protection unit, the LPU, so that most of the energy goes into the LPU and very little of it goes into the radio. So this pulse, this 4 kilovolts, 10 microseconds rise time, 700 microseconds fall time, typically about 200 amps, is a standard test which is determined to simulate what lightning strikes can cause in terms of the surges on cables. So here is a piece of equipment under test. In this instance, we're testing at 2 kilovolts, and as I mentioned earlier on, the equipment is tested and shown to withstand 2 kilovolts without current flow. In other words, the isolation barrier isn't breached. If we were to test at a higher voltage, then we would need to add an LPU or some form of surge protection to the system. So it'd be useful to consider, how do our surge protection devices work, because they are one part of how we protect the radio, how we take that damaging surge voltage and current and dissipate it in a way which routes it away from the radio and dissipates it in a device which is intended to be able to handle that type of surge. So here we have an example typically of the components that you have within a surge protector. A attached to each of the Ethernet wires. So we've got 8 Ethernet wires here, and each of those wires has a pair of diodes in a bridge form attached to it, such that positive pulses will go through the diodes on the left down to the large Zener at the bottom there, and negative pulses will transfer through the diodes on the right, and through the other Zener. So those devices are able to handle very high currents for short periods of time, which, as we saw from the previous slide, we're looking at a pulse period of about a millisecond or so. So what these surge protection devices do is to limit the voltage on any of those pins. They clamp it to ground, in effect, and make sure it doesn't exceed typically about 200 volts. So that's an order of magnitude less than the breakdown voltage that we've already determined the radio is capable of withstanding. So as I mentioned, the radio can survive the 2 kV surge, and so when we have that radio on the tower, then providing our surge doesn't exceed 2 kV, everything should be okay. But we're not in control of how near that lightning strike is, or whether indeed the tower itself is hit. And so we need to add some external protection to assist. So if we did have a strike on the nearby to the tower, then we would end up with perhaps not 2 kilovolts, but 4 kilovolts, and the current would flow up the drop cable. It would flow across the isolation boundary, because that is only capable of withstanding 2 kilovolts, and we have a 4 kilovolt surge, and it then flows into the Ethernet PHY in this instance. That Ethernet PHY is a low current device. It's made in a 40 nanometer geometry. It's just not designed to withstand the sorts of voltage and current that would be impressed on it by a surge. And so the inevitable happens, which is the PHY itself has too much current flow through it, and damage becomes catastrophic. So in the case then where we have fitted an LPU, then our 4 kilovolt surge again travels up the drop cable, and this time is diverted by the LPU and flows to ground. And the voltage that is seen and passed across to the radio is of the order of 100 to 200 volts. And as I've mentioned before, the radio is quite capable of withstanding that voltage. So our system is saved, our system is protected by the addition of this LPU, surge protection device, ahead of it. Here we can see an example of 2 surge protection devices. So typically they use either gas discharge tubes, which work based on ionizing a gas when the voltage goes too high or exceeds a breakdown voltage across that junction within the device. And the device, the device will actually glow, flash when the surge is being absorbed. So gas discharge tubes is one way, silicon or semiconductor devices such as Zenas and diodes is the other way. And sometimes, as in the example on the left here, we have a combination of the two. Gas discharge tubes tend to be slower acting, and the electronics would be sensitive to the initial edge of the surge. And so a silicon part is also used in the design in order to catch the leading edge, and then the heavy lifting is done by the gas discharge tube, which takes the brunt of the energy. In the board on the right, again we have diodes which are used to steer the pulses onto the four large devices in the middle there, and to ground via the other two devices on the left. And these absorb, again, all the energy. And the energy is, or the capability of the device is measured in kilowatts, basically. We can think that the surge only lasts for perhaps a millisecond, but maybe we have 200 volts across it, and we have 100 amps traveling through it. And so you could end up with 20 kilowatts of energy to dissipate somehow. And so the devices would have a 15 or a 20 kilowatt rating, but because they only dissipate it for a millisecond or so, the actual energy dissipated is much lower than the kilowatt rating would imply. Okay, so surge protectors are one part of the story on how we protect our systems. In a way, they're the backstop. The energy has got into the cabling. We've got to get rid of it somehow. We dissipate it in the surge protector. So how can we stop the energy from getting into the cabling, into our onto our Ethernet pairs? How do we stop it getting there in the first place? So by shielding the cable, we can effectively create a cocoon around it, which keeps those wires protected from the larger currents. They live within a sort of Faraday shield. So with a shielded cable, we can hopefully put most of the current into the shield and it goes straight to ground. And because the voltages involved are low, because we have low resistances, then the amount of power dissipated in our cabling, in our connections, is very low as well. So I've got some examples, some pictures here of various forms of cable that we might come across in our installations. So we want a shield which covers the whole cable. We want it to have good conductivity, to carry that current well, and we want to be able to bond that shield to ground at regular points at the top and at the bottom, and depending on the height of the tower, along the tower itself. So on the left we have an example. We've got our RJ45, the jack. We then have a copper coated metal shield on it, which gives it robustness as well as conductivity. And with the gland that's shown there on to the right of the cable, we've got some spring fingers which make good contact with that copper coloured sheath and conduct the current flowing in that sheath to the fingers and then to ground via the gland itself, which is screwed into the equipment, the radio. I've got a picture there of a screened cable, and this is pretty well as good a way of protecting the inner cores of the cable. A little trickier to make this off effectively. We've enclosed the screen there underneath the connector, the back shell of the connector, so that's been crimped on, and we need to find a way, which we can do with the gland on the left there. We need to find a way to get that energy that's flowing in the outer again down to ground. So that's a reasonable solution. Then we have a cable which uses a foil screen and a drain wire. So I mentioned earlier that the currents that we're looking to intercept here are in the hundreds of amps. Our foil screen is an aluminium screen. Generally speaking, it has an oxide layer on one side, and on this one you can see that there is a blue plastic coating on the other. And then we have a drain wire which is associated with it. These are quite difficult cables to make effective connections to. The aluminium is difficult to connect to make a reliable long-term connection to, and the wire itself, the drain wire, is low current and fiddly to deal with. So not a good solution. And then on the right we have a unshielded pair, which I'm afraid is it just doesn't provide us with any form of way of carrying away the surge current. So really we're looking at the two methods on the left here. So as I mentioned, we have a current which at the moment is going into just the inner cores of the cable. We want to make that current really be in the outer of the cable. So with our screened cable, we've now a situation where most of the current is induced in the outer and it flows harmlessly to ground. Residual surge, some of that's coupled into the inners of the cable, then is intercepted by the surge protector in the normal manner. But what we've done here is to reduce the burden on the surge protector, or to put it another way, we've increased the capability of the system to withstand surges. So here we've brought it all together. We've got our drop cable is screened. it connects directly to our LPU via a gland which causes the current to flow from the screen into the body of the LPU and then through the grounding cable to the radio and ground. And we have a good bond then also between the LPU and the radio itself on the screen, and the cores are carried through into the radio. The LPU has ensured that the cores don't have a voltage which exceeds the 2 kV withstand voltage of the radio, and actually is more of the order of 100 to 200 volts. So we take all those things together. Then we have the lightning protection unit, surge suppressor of some form. We have cable shielding. We have a radio which has a known withstand voltage. So those components in themselves will help us to get a good system, a robust, resilient system. But it's important that we connect them up correctly. And it's important that we site the radio, that we site the equipment itself correctly. So here we have a picture of a tower. Now it could be that we're installing on a tall building, or it could be we're installing on a comparatively low level building. But all these components are an essential part of our system installation. So at the top of our tower we have a finial, something which is there to, well, it has two functions. Initially, it will attempt to discharge some of the energy from the cloud, from the surge or the lightning that is latently in the cloud, ahead of a full-blown strike occurring. And so there's maybe an initial lower level of discharge that's occurring, which is reducing the pent-up energy. But eventually the strike will occur, and the finial then takes the surge current from the lightning strike and feeds it to ground via the lightning conductor that's on the mast. The tower itself should have a tower ground system, so it should have its own bus bar, copper bus bar, that runs along up the tower and allows for connection of equipment to that bar. Then we have ground cabling from our equipment, from our LPU and our ODU, and we will make those connections to the tower ground system. We fit a surge protector at the top next to the radio itself, and then we're using a shielded and grounded drop cable. So in the example that we have here, we have a cable running from the ODU to the tower ground system, and one running from the LPU to the ODU. And sometimes it is necessary to have a cable running from the LPU to the tower ground system as well. So this ensures that the surge energy is transferred to ground, to the tower ground, to the local ground at that particular height of the tower. Our shielded and grounded drop cable, so the shield goes into the LPU as we've seen before, and we've made that off using a gland which will conduct the energy to the case of the LPU, to the cable, the ground cable on the LPU, and then to ground. And also at regular intervals we'll connect the shield of the cable to the tower ground system in order to conduct the surges from the shield into the tower ground, and to make sure that we don't have high voltages, surge voltages, building up between the cabling and the tower itself, which could cause breakover of the insulation on the cable and damage to that cable. So we come down the mast then with the drop cable, and we come down to the equipment hut at the bottom. So we have to apply surge protection and grounding to the equipment at the top of the mast. That's the obvious place. But we have to apply it to the equipment in the equipment hut. And the reason for this is that we've provided essentially a conductor to bring surge voltage into the hut from the outside world. And that surge voltage will destroy equipment inside the hut. And then, of course, we have the risks to people who are operating in that hut. So we have to protect the equipment, we have to protect the people by having a surge protector at the building entry point in the hut. And typically this would be within about 600 millimeters or 2 feet of the building entry point. And again, we connect the protection unit to ground. We have a ground ring which connects both the tower and the equipment hut together to make sure that we don't get a difference in potential between those two constructions. The LPU inside the hut then will clamp the voltage, any surge voltage occurring on that drop cable, to 1 to 200 volts, as it does at the top of the mast, and the equipment within the hut will be readily able to tolerate that. So in detail, at the ODU, we have direct connections to the grounding bar on the tower itself, and we connect the drop cable using a grounding. Obviously, we have to take the outer off the cable, and we make a direct connection then from that the exposed screen then to the grounding system. And this perhaps is one of the areas where the corrugated screen I showed earlier is perhaps more resilient to this form of grounding than maybe a braided screen would be. And making off a ground against the aluminium foil and drain wire, of course, is very difficult. We need to make sure this is waterproofed, so self-amalgamating tape is used to seal up the drop cable where the grounding strap has been connected. And then in detail at the equipment hut, as I mentioned, we have something of the order of a maximum of 2 feet between the bottom LPU and the building entry point. We have a grounding system within the hut, and we connect that LPU to that grounding system. So we can come in on a well shielded and screened cable. It takes the surge to ground, and just popping back a moment, we'll have grounded the screen of that cable before it enters the building at the building entry point just here, to make sure that the outer doesn't carry significant energy into the building. The energy is fed to ground before it gets into the building. And then the cores of the cable, the energy on those, any energy that remains on those, is carried to ground by the LPU inside the equipment hut to the local ground system within the hut. So the residual voltage, as I mentioned, would be 1 to 200 volts from the surge, and whatever network equipment happens to be in the hut should be capable of tolerating that level of voltage. I've shown something which looks like a PIDU here, but an Ethernet switch, a PoE switch, would have a nominal 1 to 2 kV withstand capability. So that is the summary of the best installation practice. So in conclusion, we have equipment that's been designed and proven to survive high surge levels, the sort of surge level that we would see on towers. But that equipment must be coupled with a good installation. So the installation has to be well thought out and implemented. We need the right grounding, cabling and surge protection devices, and with those with the combination of those components, we should end up with a robust and trouble-free communication system. There is a caveat, which is that at some point we will have a surge event on that tower that just melts everything. But for many of the surges that occur, we've provided a significant improvement in the robustness of the system. And that is my presentation. So I'd like to open the floor to any questions that are out there.
Hi, Tim. So there were a few questions that came in. The first one says, I remember hearing that only one end of an Ethernet cable should be connected to the ground, not both ends or multiple points. There was a comment made to him that multiple points turns the cable into an antenna for noise. Is that comment true?
So we have to ground the cable at frequent points down the tower We have to ground it at the bottom and ground it at the top in order to ensure that the surge energy is sent to ground, and also to ensure that we don't get a voltage occurring between the cable and the tower, which could be kilovolts and could cause the breakdown of the plastic outer of that cable. And that would cause considerable damage to the equipment connected to that cable, the cable itself, and potentially the tower as well. Now, as far as noise is concerned, an advantage of a screened cable is that we're putting it in a noise reducing environment. An Ethernet signal is a differential signal, and so it carries a high level of noise immunity in any case. So I would expect that tower runs of up to the nominal 100 meters of Ethernet would be fine, and we see a lot of evidence that shows that that's the case. I hope that answers the question.
And there was a follow-up question made by the same person asking how many feet should be between the intermediate ground cables along the shielded Ethernet cable.
I take that as how many times what interval should we ground the drop cable as we bring it down the tower. So this is where it gets a little bit hazy in that different countries will have different electrical codes and will mandate different intervals on the grounding points. Typically, we look at something of the order of 10 meters every 10 meters, but some countries will indicate that for a 50-meter tower you should have a grounding point at the top, one in the middle, and one at the bottom. So that's 25 meters. So it depends on the country codes, electrical codes, that is.
There's another question that says, how would they do this when using power over Ethernet switches like Netonics?
So the power over Ethernet switch will apply so we have Ethernet data traveling on the drop cable, and we also have power being applied by the Ethernet switch to that drop cable. And so one or two pairs would have the supply positive and one or two pairs would have the supply negative. Now, those are on the 8 Ethernet wires. So we can ground the outer of the cable because they're not connected, they don't touch the Ethernet wires, it's just around the outside. The lightning protection unit, whatever surge suppressor, needs to be PoE capable, and it will then have the ability to pass the 56 volts, or whatever voltage is used, typically it's 56, through to the radio, whilst maintaining the surge capability, because the voltage that is residual when the surge occurs is of the order of 1 to 200 volts, and so the PoE voltage doesn't contribute to any continuing current flow through the surge protector.
We have another question asking, how would a fiber and DC powering change the grounding locations?
Okay. So fiber. Fiber shouldn't need any consideration for grounding. I'm assuming that the fiber cable itself is non-conductive, and I'm assuming that it's in a non-conductive cable sheath, unless of course we have a fiber and power pair as a composite cable. Now if that's the case, then I would recommend that we have a cable with again a shield on it. We ground the shield using the same methods as we've been discussing earlier in the presentation. And then the power wires would need to be taken to a surge protector of a form which is designed for the powering method being used. So if we assume that that powering method is a voltage lower than 60 volts, cell voltage, then there are a large number of surge suppressors which will handle that voltage, pass it through to the radio whilst taking the surge energy to ground.
There was another question asking for PTP 670 ODUs that employ external dish antennas. Is it required or recommended to use coaxial surge suppressors on the vertical and horizontal antenna ports when connecting to coax jumpers?
So the radio itself has a ground, a grounding element internal to it, and I think that we specify a maximum cable length of about 2 meters on there. So typically one would, if necessary, depending on the length of the cable, ground the cable at an intermediate point, although if it's 2 meters long, then you should be able to manage without that. If we're looking at longer cable lengths than that, then we start to run into an area where the use of some external surge protector becomes required. I'm not sure exactly at what cable length we would decide that that had to be done.
There was another comment saying that they had read elsewhere that armored cable did not provide electrical shielding, just physical strength. Would that be true?
Sorry, that what cable?
Armored cable?
Oh, armored. I think this depends on the armoring. So some armored cables have strands of steel wire wound into the outer of them, and that provides the electrical strength, but would not be a good way to, it doesn't form a good covering around the cable. So I think this depends on the type of cable. A cable where we have a continuous shield around it, metal shield, that should provide the current flow and protection for the inner wires.
There was another comment asking if they can use the same cable from the top of the tower to connect the ground for LPU and ODU.
So we have a drop cable from the LPU to down the tower, which would have a shield on it, and we have a cable then which is going from the LPU to the radio, to the ODU, which shouldn't be longer than about 2 feet, or shouldn't be longer than 2 feet. I would have thought that that would be best made from the same type of cable. I can't think why one would want to use a different cable to connect from the LPU to the radio.
And that
So
looks like,
I think the answer is, yeah, I think the answer is yes, it should be the same cable type.
okay. And that looks like it's it for questions. If you wanted to say anything else.
No, I'm done. I don't know whether we have a way of people sending questions, but I'd be very happy to answer questions by email or whatever means. If people have further questions and queries that they'd like to discuss. It's tim.wild, that's tim.wild at cambiumnetworks.com. But, well, thank you very much, everyone, for listening. I hope that you got from this what you wanted. And as I say, if there are any questions, I'll be very pleased to try to answer them.
All right, thank you, Tim. A copy of the presentation and the webinar recording will be available on the Cambium Network's online community. Thank you for joining and have a good day.